Okay, so we are doing 7.3 today. We've done 7.1, 7.2, which was all about the law of sines. And so now we're going to talk about the law of cosines. The law of cosines is nice because some of our triangles get to be a little bit crazy, and the law of sines isn't really going to help us. Specifically, the law of sines doesn't help us if we have a side-side-side triangle or a side-angle-side case. And so that's when you're going to use the law of cosines. But before we talk about the law of cosines, it's nice to recognize this length restriction on the triangle sides. And basically what this says is that, it's not what it says, basically, it is what it says. In any triangle, the sum of the lengths of any two sides must be greater than the length of the remaining side. So if you add up the sides, any two sides of a triangle, it had better be bigger than the last side that you didn't add. If not, then it's not a triangle. It's not going to work. And so this is important because, as we will see today, that's not always how your triangles are going to look, and they're going to cause you issues. We kind of saw that with the handout from last time for the law of sines. Remember how we had the ambiguous case where sometimes we had this dinky little side length and it didn't ever work. It didn't connect over to the other side length. And that's because it didn't actually stick with our side length restriction. That third side didn't ever connect because it was always too short and the other two sides were way too long. So our law of cosine says that in any triangle ABC, where we know the sides are A, B, and C, then we get these three different little laws, where we have A squared equals B squared plus C squared minus 2 times AB cosine A. So what's important to note here, because they're all slightly different, is that if I have an A squared, then I'm squaring B and I'm squaring C, I'm adding those together, and then the minus 2 will always be the B and the C, like the two things that you squared here. And then the cosine, the angle, will always be of what's on the left. So they follow a pattern of sorts. So when I have B squared, I'm going to have A and C that I'm squaring and adding together, minus 2AC times cosine of B. And then the same thing for C. I know we're nearing the end of the semester and we're getting close to finals. You will have an identity sheet for the final exam. I'm not going to not let you use that. Like I mentioned before, though, there might be a page of it where I don't let you use a calculator. I'm still not quite sure how that's going to look yet. But you will get an identity sheet for at least most of the final exam. So I'm not going to expect you to memorize the law of cosines. I would hope you can memorize the law of sines. That's not super complicated. And the Pythagorean theorem, I hope you have that memorized, which is actually just a special case of this law of cosines. Because what happens is whenever we have A squared plus B squared equals C squared, in this case, our C is opposite, it's our hypotenuse, which is opposite of our 90 degrees. Well, what's cosine of 90 degrees? 0, which means all of this stuff over here, this negative 2AB cosine C, drops off, leaving us with C squared equals A squared plus B squared. Oh, I didn't notice that. So the Pythagorean theorem is actually just a special case of our law of cosines. It falls straight out of it. Are we ready to see what one of these looks like? In a minute, maybe. Still see some people writing. So all the triangles that we are going to talk about today are going to be side, side, side situations or side, angle, side. Remember 7.2 was all of our ash triangles, our side, side angles, bless you. And then the time before that was the others, where we had our laws of congruency that we were able to use with those. Are we good if I move it? Okay, we're going to do the first example on the handout. That's what we're doing next. It says a surveyor wishes to find the distance between two inaccessible points, A and B, on the opposite sides of a lake. While standing at point C, she finds that B measures 259 meters and A measures 423 meters. We need to find, I can't read today. An angle ACB measures 132 degrees 40 minutes. Find the distance C. And then they give you this lovely picture of the lake, and they show you how exactly this is all being figured out. And so we need to find the distance C. So if we need to find the distance C, notice that the one angle that they did give us lies opposite of side C, which means we know angle C. So if we know angle C and we know the measure of A and B, then we're going to use that last version of our law of cosines, where C squared equaled A squared plus B squared minus 2AB cosine C. Because when it comes down to this version of our law of cosines, we know A, we know B, and we know angle cosine or angle C. So the only thing we'd be missing is that side length C, to where it really becomes a plug and chug situation. Because C squared is going to be, well, A squared is 423 squared. Obviously, you're going to want a calculator for these. I do not expect you to do these by hand. Minus 2 times A, which is 423, times B, which is 259, times cosine of 132 degrees 40 minutes. You do have to convert your your minutes into degrees. So that is something you have to do before you type it into your calculator. Remember that in order to do that, you take the 40 minutes and you stick it over 60 because there's 60 minutes in a degree, meaning you get 32 and point, what is it, 6666 forever, ever, ever? That's a weird 3. So you're going to type all of that bad stuff in, and then you're going to square root it. And we are going to round to the nearest meter. We'll see what you guys get and see if it's the same thing I got. Has anybody gotten it yet? 628. Yeah. 628 meters. You can do it doesn't check to make sure your answer is 100% accurate, but if you add the 423 and the 259, based on our triangle side length restrictions, that had better be greater than what we just got. And so you can do kind of a very general check just to make sure that your answer makes sense in terms of the side restrictions, which 259 and 423 is greater than 628. So a lot of your problems will look like this, where they give you literally everything you need, and you just plug it in Obviously, there's a lot to plug in. You do have to do a conversion over here to convert from minutes to degrees, and then you have to take a square root. But it really does become a plug and chug problem. Are there any questions on that one? Okay, here's your next example. We're going to solve some triangles. Sorry, I'm going to pull down everything so that it works. Solve triangle ABC if angle A is 42.3 degrees, side B is 12.9 meters, and side C is 15.4 meters. So they told us we have angle A, angle B, and angle C, because if we're solving this, we have to come up with every bit of our triangle. Side A, side B, and side C. So we know angle A is 42.3. We don't know any of our other angles. A lot of times I like to go ahead and list everything kind of together like this so that as I'm working through, I kind of know when I'm able to stop, because it'll be when I know every single bit of information based on this triangle. Now, when we're solving an entire triangle and we're dealing with our law of cosines, we may have to use our other stuff, like our law of sines. We may have to use that our interior angles equal 180 degrees and everything else that we've already been using in Chapter 7, because we have to find more than just the last remaining side length. But if we are given this information, notice we have an angle, a side, and a side. Don't just immediately think, oh, well, this is that bad situation, the ash triangle that we had in 7.2, because that's not what we have, because we have the angle that lies in between these sides. So we actually have a side angle side situation, which I told you all of your examples today will be side angle side, or they're going to be side side side. That's when we use our law of cosines. So what's the one angle they gave us? Well, it's angle A. And they gave us side B and side C. So we can actually use the A squared equals B squared plus C squared minus 2BC cosine A to help us find the side length A, because we know B, we know C, and we know angle A. So anytime you're approaching any of the problems really from any of Chapter 7, you're going to be looking for what is one bit from one of these different laws. I know 3 out of the 4 parts of it, so which one am I missing? And that's where you're going to start. I know 3 out of the 4 letters in this one, so I'm going to solve for A. And we're going to round to 2 decimal places. And if you need help figuring out how to type some of this stuff into your calculator, I can show you after class. When in doubt, stick things in parentheses is always what I say. All right, did you get 10.47? Bless you. Now that we have all of our sides and we have one angle, we can do our law of sines to come up with another one of our angles. Because if I have side A and angle A, then I can use that, let's say with side B, to figure out what angle B is. Because remember, law of sines is A over the corresponding side of that angle equals B over sine B. So now that I know what A is, I can figure out what angle B is. Because this was 10.47, 42.3. B was 12.9 over sine of B. So you get sine of B equals 12.9 sine 42 over 3. Sorry, here you go. But remember, if you type it in like it is right there, that's going to give you some sort of a decimal, like a really crazy decimal, because that's sine of B, so you have to take the inverse sine of all of this jazz in order to come up with actually what B is. And I'm going to round to the nearest degree. On your homework and quizzes, it will be very specific on what to round to, and when it comes to any type of a test, I will always tell you exactly where I want you to round to, so there won't be any question. And if I ever leave it ambiguous, I'm always very gracious when it comes to the grading on it. Like if I didn't tell you to round to the nearest degree and you had 56 point whatever, I would give you credit for that as well. But I will make sure that my test is detailed in which answers I want you to give. So now we have almost everything. Theoretically, you can do the law of sines again, like using the A over sine A equals C over sine C, and you can do the exact same process again in order to get what C is. I think using the interior angles that equal 180 degrees is a lot easier because you're doing addition and subtraction instead of doing all this multiplying, dividing, sine inverse, blah, blah, blah. So for me, if I'm ever given the option where I can do A plus B plus C equals 180, I'm probably going to do that over the law of sines. And now that we know A and B, I can come up with C pretty easily. Only when I know the measure of all three sides and all three angles have I actually solved the triangle. Are there questions on how we did any aspect of this? Notice we start with the law of cosines. Once we've done the law of cosines, then we did the law of sines, and then theoretically you could have done the law of sines again, or we used the interior angle aspect to come up with our last angle. It kind of follows that pattern every time. Regardless if you're dealing with a side angle side triangle, which is the one we just did, or this triangle. Notice we don't have any angles, which means this is a side, side, side triangle. We just know our measurements of all of our side lengths. So this one's different than the other ones we've had because the other ones we had at least one angle. Now we have three sides. All of our laws of cosine deal with an angle. So what do you think we're going to do? Can we still use our law of cosines even if we don't know an angle? Yeah, we can. The reason why we can is because we know all the side lengths. Before, when we were trying to come up with our missing side length, we knew the angle, and so it worked out. Now, regardless of which one of these we want to use, what we're missing is the angle. So we can manipulate and move things around to where that's what we're trying to find because we know all the other information. So theoretically for this problem, because you know A, B, and C, you could use any of these to come up with either angle A, angle B, or angle C to get started with. The notes in the book started by finding angle C first. Why? I have no idea. But that's what I'm going to do because I have all the calculations for that. Okay? But no, you could start finding you could find angle A or B first and it wouldn't change the process at all. So I'm going to start by finding angle C. So that means I'm going to use C squared equals A squared plus B squared minus 2AB cosine C. And before I plug anything in, because I don't want to do any of that, I'm going to focus on getting that cosine C 100% by itself. Then I'll start plugging in values. But until then, I'm going to leave it in ABC form. So if I'm trying to get cosine C by itself, well, I'm going to subtract the A squared, and I'm going to subtract the B squared. I'm doing algebra here. And then what would I do if I'm trying to get cosine C by itself? Divide by negative 2AB, correct. Yeah, there's that negative there, so I want to divide by all of it. So when I do that, I don't really love leaving that negative down there, so I'm going to apply that negative to everything on top. Okay, that means all the signs on top change, but that allows me to get rid of that negative on bottom. I'm also going to do a little bit of reordering so that my letters on top are in alphabetical order. So if I'm finding the value of C, I'm going to end up taking the cosine inverse of all of this stuff. Is really what I'm doing. Like if you want to do one massive calculation, that's what you're going to do. You're going to type cosine inverse of A squared plus B squared minus C squared all over 2AB. That's what you're going to do all in one big, get it in and get it done. If you don't want to do that, you would do all of this part first. You're going to get a decimal equivalence, and then you're going to have to type the inverse cosine of that. Either way, you're going to get to where you need to go. Only at this point would I write down on my paper now and fill in with the A's, the B's, the C's, and all the different values. So that I have cosine inverse of A squared, which is 9.47, plus 15.9 squared, minus 21.1 squared. 2 times 9.47, 15.9. You might have to be careful when it comes to this minus 21.1 squared, depending on how you type that in and what kind of calculator you have. If you type it in like this, it may give you a positive solution because it's going to think that what you mean here is this when that's not actually what you mean. So you may want to put a little set of parentheses around that. That's one of the reasons why I do so much of my math on the paper and don't rely as much on the calculator, because some calculators do calculate that differently. In my college algebra class, I always show them, depending on the calculator you have, if you type in negative 2 squared versus negative 2 squared, most of your calculators will give you the same answer for those, and those are different things. This top one gives you negative 4, this bottom one gives you positive 4. But most calculators will give you a positive 4 answer for both of these. And so you do need to be a little bit careful for right here. Anybody want to be daring and tell me what they figured C to be to 1 decimal place? That's exactly right. 109.9. High five you. Because that's a lot of crap to type in, and I get that. But yes, angle C is 109.9. Now here's the nice thing. Once you've done all of that to find one of your angles, and it, like I said, it wouldn't matter if you found angle A first, angle B first, or angle C first, because you're doing the exact same math. Once you find one of your angles, though, now you know the angle, its correlating side, and you could find either one of the remaining angles by using your law of sines again. So even though this problem is different because we had side, side, side instead of side, angle, side, we still start with our law of cosines, then we're going to move on to our law of sines. And then you have the option after that to use your law of sines for a second time or use the interior angle aspect. I'm going to go and find angle B next. You could find angle A next. It's whatever you choose. That's going to be sine B by using my law of sines. And I'm going to round to 1 decimal place again. You guys get 45.1 for B and then 25 for A. Were you just banking on my calculator skills? That's also okay, because I got them out of the book, so I did double check them though, because the book can be wrong sometimes. Regardless of whether you start knowing one angle and 2 sides, or if you start with no angles and 3 sides, you're going to do your law of cosines first. The law of cosines can either give you that remaining side that you're missing, or it will give you one of your angles. And then from there, you can do your law of sines, and you can use your law of sines again, or the interior angle rule. We're going to do one where they give you a picture. And then we're going to switch topics for one problem. Are we good if I move this so we see our picture? This one, they're going to give you a triangle. And they're not going to ask you to solve it. They're just asking you to find angle B to the nearest degree. So they're only asking you for one thing. Angle B to the nearest degree. So if they give you all three sides, which they do, and they want to find the angle, then you're going to use your law of cosines that has that cosine of that angle. So if they're wanting angle B, then we're going to use the version of our law of cosines that deals with cosine B, which is our B squared one. I guess I can do it over here. B squared equals A squared plus C squared minus 2AC cosine B. That's what we're going to use, because we know everything besides angle B, and that's what they wanted us to find. Now, how do you know which side is which? Because it's going to make a difference because we have B squared over on the left. So how do we know which of these is side A, side B, and side C? That's exactly right. You're going to be opposite your different angles. So side B is opposite of B, side C is opposite of C, and side A is opposite of A. Then it just becomes a plug and chug problem. I'm going to go ahead, since I know I'm solving for my angle, before I do my plug and chug, I'm going to do that manipulation where I move everything around again, and I have cosine all by itself. So I get cosine of B equals A squared plus C squared minus B squared all over 2AC. That way I can either plug in everything and then do the inverse cosine, or I can do inverse cosine with all of my numbers already sitting there. Oops. And it says round to the nearest degree. So we'll see what you guys tell me it is. Anybody daring enough to tell me what they got? 33. Good job. 33 degrees. So the big thing there is if they give you a picture, just knowing that the side is opposite of the angle. If you flip over your handout, on the back is a really nice table that actually talks about all of the different types of oblique triangles that we've covered in 7.1, 7.2, and now 7.3. The case 1 are the ones that we talked about in 7.1, where really we just had to use the law of sines. So case 1 is from 7.1. Case 2 is from 7.2. That's the ambiguous case. Those are our ash triangles, or side-side angle ones. Those ones were dependent, and we would sometimes get 0 triangles, 1 triangle, or 2 triangles that worked. Cases 3 and 4 are the ones that we've seen today. These are the ones from 7.3, where we had side angle side, like our very first 2 examples, really. Yeah, our first 2 examples. And then these last 2 examples have been the side, side, side. So this is a nice, concise table to kind of walk you step by step through, where you can see where we're using law of sines, or we're using the law of cosines, or the interior angle thing. And there it is for the video. So, nice little table, has all your cases, and kind of walk you through it. So, that's a good reference page. I shrunk it a little bit and stuck it in the middle of my notes as well. So if you open up the notes, it's there in a slightly smaller format. Okay, the last topic of this section and of today is Heron's area formula. We use this with our side triangles. If a triangle has sides of lengths A, B, and C with a semiperimeter equal to S equals 1/2 times A plus B plus C, then the area, which is done with a cursive A or a funky A, however you want to look at it, of the triangle is equal to the square root of that semiperimeter times the distance of the semiperimeter with each of its sides. Is basically what that says. So square root of S times S minus A times S minus B times S minus C. And yes, when you take the square root of a number, you do get a positive or a negative, but since we were talking about area, we don't think about areas in terms of negative. So we're only thinking about the positive square root. As much as my husband would like to think that we don't have a yard to mow, we do have a yard to mow. There is an area. We don't get negative area just by square rooting it. For as much as we're going to do with Heron's area formula for our side triangles, these are going to be plug and chug. And we're going to do one example of them. All right, you ready? Can I move it? I don't hear anybody screaming no, so I'm assuming yes. So the area problem is the other example that's on the front side of the handout for today. It says the distance as the crow flies. So I don't know if you guys have ever heard that terminology, but distance as the crow flies means you're ignoring like roads and routes and things like that, and you're literally thinking about the shortest distance from point A to point B as if you could fly over everything else, any other obstacle that might be in your path, because crows can do that. So the distance as the crow flies from LA to New York is 2,451 miles. From New York to Montreal, it's 331 miles. And from Montreal to Los Angeles is 2,427 miles. What is the area of that triangular region having those three cities as your vertices, obviously ignoring the curvature of the Earth, because that would change things. So I would totally recommend making a triangle, like drawing a picture. You don't have to. You could just assign A, B, and C to each of these. That's fine as well. But in case you're a visual person like I am, I like to draw a triangle where I have LA, New York, and Montreal. They told me that LA to New York was 2,451, New York to Montreal was 331, and Montreal to LA was 2,427. Now, we're not doing anything with angles on this because we are finding the area. So I'm going to call one side A, one side B, and one side C. Literally does not matter which one you call which at all. So if I have to find the area, that means I'm going to use Heron's area formula. But in order to use Heron's area formula, I have to know my semi-perimeter. which is S equals 1/2 times A plus B plus C. So I have to calculate my S first. 1/2 times 2451 plus 331 plus 2427. 2604.5 is my semi-perimeter. Once you know what your semi-perimeter is, you can find your area. Because Heron's area states that you're going to take the square root of S times S minus A, S minus B, S minus C. So we're going to plug in all the information that we have. (2604.5) times 2604.5 minus. This gets a little bit long just because your numbers are a little bit long for this problem. So I'm going to jump down. Know that this is still multiplying. I just want to be able to show everything on the screen. So that's still included underneath and being multiplied. .401,700 miles squared. You're going to really like your calculator in this section.